GM. Today, welcome to the Uncle Founder first. And today we'll be going over just like it's be a continuation of Alpenglow we were talking about last time. So let me try to share the link to just get people in the chat here. 1 minute. So guys, right here. Alpenglow. Uh, 1 minute. 5. Okay. Trying to share to everybody so everybody can come, but yep. Live now. Alright. Okay, so let me share backstage. If you like to be backstage, just show your interest in the chat and I can bring you up also. What else I want to share? Okay, add invite guest, copy. Yep. Want to talk Alpenglow. Message. Join backstage. Or just wanna chill. Just wanna hear us chat. Okay, let's see. One more thing to do, and we should be good to go. Oh, sorry, typo. Share backstage. Share. Yeah. Okay. I think we have to go now. Okay, so let me bring up the white paper first to know what that is. Okay, this is where that one was. Yeah, I'm still on page 13. Crazy. So let's see. If you missed the last episode where it was just me rambling and trying to figure out what this was about, I'll probably drop a link to that in the chat. But if you want to, I should probably keep an eye on this. Where's this? How do I know if someone wants to join chat? Okay. Okay. So yeah, I was saying if you were not here on Monday, that was where we started talking about Alpenglow. So let me do like a quick recap of what that's about. We talked about Alpenglow is this new consensus proposal uh, on how to increase finality, increase bandwidth, and reduce latency, basically IBRL. So how to land transactions fast, how to make sure transactions that are sent actually increase the speed of when transactions will be finalized. That's basically what all of this is about. Then now getting into the meat of it, there's two things are involved in Alpenglow. That's the votor and the rotor. So let's talk about this. Can put this here. Okay. So there are two things involved. That's the votor and the rotor. Those are the most important part of what Alpenglow is proposing. That is the voting component, that's the voter, and the broadcasting component, that is the rotor. This is too loud. I think it's actually good, not too loud. It's a chat. Okay. Good. So let's drop in chats in DMs. Yeah, I should probably get a second monitor so I'll be able to check everything at the same time. Okay, so let's just get into what the voter and the rotor is about. Now I can explain it confidently since I've gone over it one time before. So what that's about is as it says, the voting component, that's the voter, is what handles voting, the new way to handle voting per se in Alpenglow. So it reaches finality fast. And what Alpenglow is proposing is there will be 2 rounds of consecutive finalization. Which means so the first round will be and will be happening consecutively. Yeah. First round is if 80% of stake votes for this transaction to pass, it gets included. If 80% of stake votes for this block to be produced, not transaction to pass, vote for this block to produce, and the block is included. Then, if for any reason, well, the second one is there'll be 2 rounds of 60% stake. So if 60% stake has voted for this transaction for this block to be included, we do another round of 60%. So why do we have to do 2 rounds of this? There are 3 assumptions of our Alpenglow. So first reason, let's say there's something wrong with the network and the network is slow. We don't have up to 80% stake available at that moment. 80% stake just means 80% stake. It's not like 80% of all the validators, it means 80% of stake weights. So if just assuming if just 10% of all validators have 80% stake, that means those 10 validators which are honest can vote for the block to be included, and it gets included right away. Yeah. But if for some reason 80% is not online, you can do 2 rounds of 60% stake voting. So yeah, and these two are happening at the same time. So like one happens and waits for the other one. Both of them are happening at the same time. So whichever passes first. So whichever has the minimum time between these two uh, consecutive finalization gets to determine how the block is included. So that's the part of voter. That is the part where each other validators vote for the block when they fully get the block that has been broadcast by. I think broadcasted should be a word. Broadcasted. Have been broadcast by the leader. So yeah, so that the how does the leader broadcast transactions? That's the rotor part here, which is how the leader broadcast. So if you don't know what leader is one validator that is selected for and the order of how randomly, so verifiable randomly function. The order of each leader is determined the verifiable random function. So you can know you can know which leader will be included in the next after this leader has exhausted their own blocks here. So the round of leader changes, and you will know, you can basically know that's what I was saying. Uh, all that explain pass, I explain leader. Okay, so a leader is one node that is selected to lead, basically to broadcast. So once transaction gets to how the transaction actually gets to a node that creates those transactions into a block, it is you can send the transaction directly to the leader with CPU, or you can send it to a validator, an RPC node, which RPC nodes now forwards it or relays it to the leader. Anyhow, it gets to the leader. So that's it. So when the leader gets those transactions, it starts including them, starts working on them at that moment. And what it's doing, by from what I've learned so far, is it has this Merkle tree. It creates a Merkle tree for each. Okay, before I get there, each are broken down into slices, and the slices are now, so we can have one slice, two slice, a third slice, fourth slice, until all the blocks, until we have a full block. So as the as the oh my God, as the leader start getting transaction, it starts creating those slices. So if you get a slice, a full slice, it now broadcasts that slice to all to the nodes on the network, but it doesn't previously. That's to send each slice to every single node on the network, other validators on the network. But now with Alpenglow, it doesn't have to do that. It just sends it to, still does that, but in a more efficient way. Yeah, it sends it it sends it based. You receive the transaction based on your stake. So if you have more stake in the game, in the network, you get more of the transaction, which more of the transaction slice, which you now have to broadcast to all other networks, all other nodes on the network. You have to gossip to, so your own is just to get the transaction, then communicate to other people on the network, other nodes on the network, and make it until they have their own full slice, and they keep doing that until a block is created. So we know that we have a slice. Then what is the slice just sent, divided and sent to each node based on stake? So the slice is also erasure coded into shreds. And erasure coding just means a method to, we talked about erasure coding every last week on Monday. It's a method um, to make sure that it's fault tolerance, right? So a method to make sure that if I have, let's say I have 10 chunks of data, and I want to send the 10 chunks over. If by any means, let's say to some amount of chunks get lost along the way, when the data arrives at the destination, it should still be able to reconstruct the 10 chunks as a whole. That's basically what erasure coding is. So what erasure coding does is methods, this formula, this algorithm uses, and the one Alpenglow uses is Solomon erasure coding. So that what that does is, have I explained everything here? I think I've explained everything here. Okay. We'll talk about Alpenglow Clear Hash Network. We will come back to this. Let me get to that important part. I will talk about all of this on Monday, so I'm just trying to skip. Uh, 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 yes, fault tolerance. Is this the erasure coding part? Not here yet. We will come back to these assumptions, but let me finish explaining what the erasure coding is. There is this list of important terms. We have epoch. Yeah. So an epoch is blah, 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 blah. We'll come back to what an epoch is. If you know, you should know that. But if you don't know that, we'll come back to it. Erasure coding, leader, timeout, adversary, synchrony, network delay, correctness. Yes, erasure code. It means this is okay. Mostly in other textbook, you see this as K, comma M. That means an erasure code can be expressed, an erasure code expression can be expressed like such. This is K, comma M. What this means is parity chunks. What parity chunks means is extra chunks, extra data that you add to this 10 chunks that I want to transfer. I've broken my data down into 10 chunks. I want to transfer all the 10 chunks. I need some other extra baggage that will be added to it that can be used to reconstruct all the 10 chunks if some of the chunks are missing. That's what this parity chunks means. So this is the parity data. This is the total number of data that's available. Total number of these parity chunks, and this is your data, the data shreds. So these are the extracts that you're trying to. So it works with an expression. Let's see if I can pull up. When I pull up what's called Excalibur. Excalibur. That's one in the chat room. Nobody yet. Excalibur. Okay. Let me bring this one in. Yeah. Yeah. Not this one, not this one. Okay. Not this one, not this one. This place. So it is K. It's mostly expressed as. Oh, have I stopped sharing my? Okay, no, sorry guys. Something different. Wait, am I sharing? One minute, guys. I'm trying to see if I'm. Okay, I'm cool. I'm trying to see if I'm actually sharing what I thought I was sharing. Well, yeah, we're good. Have an expression like such k so I'm going to say k is the number of data chunks, and m is the number of parity chunks. I also attached a video on Monday that you can watch to understand what erasure coding just means. So let me just try to do it again. So how this works is for you to know. Okay, this is it. There's something called an expansion ratio. So and that is defined by k plus m divided by k. So total number of chunks plus parity chunks divided by total number of chunks. So that means from this paper, this is total number of chunks. This total number of data chunks, and this is total number of all the chunks together. Data plus. Well, we'll look at it now. I'll come in 1 minute. So that is k plus m. Let's say this is equal to let's call this g. Yeah. So say k plus m equals g. Okay. So k equals g. So let's say that. Let's assume, or let's say k plus m is equal to g. Let's do it that way. 1 minute. Just trying to, let's say, let k plus m equals g. So we can now re-explain this as g over m is our expansion ratio. Yeah, so that is what this is saying here. G over m. So if you look at the explanation, say for integer, I think this row and all this Greek alphabet. Erasure code encodes a bit string m. So we have a string m, big M or size small m, into a vector of data pieces d1. So you have a string, and the size of the string, you erasure code that string into a vector of data pieces d1 up to d row, and there's a size. Okay, forget that one. Right, blah 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 blah. Erasure coding makes sure that any data pieces may be used to efficiently reconstruct m. So that means this is parity, exactly. Any parity data piece may be used to efficiently reconstruct m. So that means you can reconstruct it from any amount of this data parity. So let's say the reconstruction algorithm also takes an input of the length m, blah 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 blah. We'll be encoding using a See read Solomon erasure code, which encodes a payload as a vector. Okay, let me show an example of this erasure coding crates. Talk about it. Erasure, I think it's read Solomon erasure. Okay. This is a Rust crate that does erasure coding. Uh, try not to explain it too much, and I'm explaining it too much. So there are different implementations. There's the one in Go, Java, Haskell, but it's basically just an algorithm. So this is a Rust implementation. So what this is so you're saying you import the crates. So we have R is read Solomon, an instance of read Solomon. When 3 is the data shards, then 2 is the parity shards. Like I said, parity shards are the extra garbage. It's called the garbage. The extra load that you're attaching to this your original data shard to be able to reconstruct it, even if any data is lost. So we say 3 shards and 2 parity shards. Yeah. So these are the first 3 shards. These ones are the extra parity shards. Then we say we construct the parity shards with R encode. We encode it with this is R is an instance of read Solomon, yeah. So we do R.encode this master copy. Master copy is just inside these shards in macro. So we've encoded this. So the aim of erasure coding is that if any data is lost, as long as we have k size, we can still reconstruct this data back. So that's basically what it's saying. So if we have total amount of data here is 5 here, that's 3 plus 2, 5. We should, if let's any 2 of these data gets lost, we can be able to reconstruct the whole original data back just by using 3 data shards. 3 shards might be data shards, might be parity shards. That's basically what erasure coding is trying to solve. So now we just collected this as a vector. Wherever was okay, we said we've encoded this data. Yeah, this one we've encoded master copy. So we are just trying to say convert it into optional type. So optional, this is sum 1, sum 2, sum 3, sum 4, sum 5. I'm converting them to optional type. That's what this is doing. So converting them into optional types here. So now we're now saying first item here and the last item here are none. So we're deleting these 2 items in the list. 1, 2, 3, 4, 5. So the first item and the last item here are none. And we will try to reconstruct it with this we have, so for some reason we lost some parts and we are now reconstructing it here. So if we reconstruct this even after we've lost some packets, so that means we need just 3. Like we said, we need just 3. Even if we lost this first 2, you can use this remaining 3 to reconstruct. So that's basically what erasure coding is trying to say. So we need k data to be able to reconstruct the whole k plus m data. So if we reconstruct this, we should assert that what we have is the same thing as what we reconstructed. So the data that we got, data that we reconstructed. So that's basically what erasure coding is saying. So that's one way you can verify that the data that is getting all to these validators are actually correct data. So if for any reason some data gets dropped, you can still reconstruct them. Yeah, that's erasure coding. So that's how the slices are broadcasted to, permit me to say broadcasted to other nodes on the network. Yeah. And if any validator is missing some part of data, it just gets them from other, let's say it gets it by gossip from other validators on the network. And once you are collecting these slices, once you are building the slices to a full block, if you have all the slices now, then you can now create okay, let's get to that. Where were we? We stopped at the voter and the rotor. So how does it now work? How does it work under the hood? So this broadcast is, should we go over? We've gotten over all of this on Monday. We're trying to see what will be important. If I miss any one of it, you'll still be able to follow along. Okay, before then, let me drop the link to the the white paper and the charts. Yeah, I say each slot has a designated leader from the set of nodes. Each leader will be in charge for a fixed amount of consecutive slots, known as the leader window. So the leader is rotating, and a verifiable random function is evaluated before each epoch to determine a publicly known leader schedule. So before the start of an epoch, we run this random function, this VRF, to tell us how many was the schedule of all the leaders that we have used in that epoch. So that's basically what I'm saying. Protocol uses timeouts. No set timeout to make sure that the protocol does not get stuck or waiting for blah 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 blah. You don't probably need this. If you don't do that, you can still get up, can still be up to speed on what's happening. Yeah, yeah. Aggregate signature. So now, what's this one we're talking about? Signatures from different signers from the company, blah 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 blah. Into short messages. Okay, so if you have this your transactions coming, you have slices, and you have built a complete slice, you built the next slide. You'll be storing all of these slices that you're building inside something called block store. Yeah, that's where all the transactions will be stored, as far as I know. Storing them in block store. Then once it's complete, you can sign on it. Yeah, and you're signing on it, and you are saying, you're broadcasting to the network that, okay, I've voted for these transactions. My signature is included on this block, not for the transaction. Voted for this block, and my signature is included on this block. And everybody just keeps communicating with each other until we have 80% stake here of validators, 80% stake that are successfully signed on the block that they want to include the block. Yeah. So once you have that, someone creates a signature that we have everything now. Everybody's vote. Now want to create a signature. And that means once the signature is gotten, so signatures from different signers may be combined non-interactively to form an aggregate signature. So technically, we only require non-interactive multi-signatures, which only enable signature over the same message to be aggregated. This can be implemented blah, 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 blah. Aggregate signature allows certificates to fit into short message. This is not one I'm explaining. Let me see. There is trying to see. There's one place that this signatures thing was explained better. If I can get it. Signatures. Say signatures. I think we have data signature. We have secure non-fungible as stated earlier. Each node knows the public key of each other node. Okay, one multi-signature, not this one. Not this one. Aggregate signing of signatures. Yeah. After blocking signatures on block resolution. Not this one. The signature. Decentralized. But not this one either. Let me see. Was it signature? Let's try signature. There'll be a lot. There is a particular comment or an highlight or something that explains what happens when everybody signs, and after the signature, that's when medical route for each slice later generates still random shoot Solomon. I think we already know this. Signature, block store, signature, Alpenglow II signature. I think it's this one. Let me just take my vote in the certificate. Alpenglow certificate message. Submission is the cumulative stake of aggregated votes in the certificate. This is not one I'm looking for. Almost there though. Is it this one? No, this one. Yeah, I think the word is not signature that I saw. Well, let me see if I can still find it. Sorry, guys. The there's this expressive word that explains what I was trying to explain in the material here, but I can't find it for some reason. Knows. Okay, so and some part of Alpenglow are already being implemented in agave. So what's agave, you ask? Another story. Let me 1 minute. I'll pull that up so you get it. I'm looking for the second slide. Alpenglow. I asked a specific reload. Something broke for some reason. I don't know why. Okay, I think it's this one. Okay. Parts. Yeah, almost there. Almost there. Almost there. Almost there. Short coding, signatures. I guess signature allows certificates fitted to a short message. Okay, almost there. The exact word. Finalized. Is it finalized? With a bandwidth of not bandwidth. It's a. I think it's just. Yes, this is what I'm talking about. Yeah, when enough votes are received. Let me search this one. Yeah. What the actual votes? Okay, it's just saying when enough votes are received, the respective certificate is generated, and when a received or constructed certificate is newly added to the pool, the certificate is broadcast to all other nodes. So as people are voting, as the nodes are voting on the block, everyone knows everyone is receiving the votes. So the first node that gets 80% stake, that validates that 80% of stake has voted for this transaction. Once it has enough votes, it constructs a certificate via from everybody's votes, constructs a certificate, and it broadcasts the certificate to all other nodes. So whichever nodes collects enough votes first, combines the votes, create a certificate, and that is the sign, that is the indicator that okay, this block is okay to include. So that's basically what that means. Yeah, so that's what I was looking for. But I still can't find it in the paper. But it was from the paper I got it by English. When certificate. I think it means certificate. Okay. Yeah. Yes. Certificate. Introduce different type of vote certificate. These are vote certificates stored in the tableau. Okay. Certificate. Okay. Yeah, we don't need to go over everything since I've explained that one already. So what is the next part? So the Merkle tree part is so that before there has to be a way for this transaction to be proven that it actually exists, that it's actually correct, and it's not like a okay. So each slice, I'm taking from the top, each slice that's constructed and erasure coded does data Merkle tree action on top of all the the slices. So it constructs a Merkle tree on top of all with all the shreds first. So once it has one slice, it creates a Merkle tree with all the shreds. Let me see if someone's trying to join. I don't know yet. Okay, no one. So it constructs a Merkle tree with all the shreds. So from the leaf of the Merkle tree to the root of the Merkle tree, constructs the Merkle tree, and it signs that root. So anybody that gets all the shreds, all the nodes that are getting the shred can also verify, get a part. So it gets also a part PATH that says this is where this transaction or this shred, this is where this shred belongs on the tree. So if you get a shred and the part does not, when you hash it, the part is not, you have a wrong part or you have a wrong shred that doesn't belong to any part on the tree, then you can validate that actually this transaction is, this shred is wrong, maybe from a malicious player on the network. Yeah, so that's the way each shred is validated that it actually belongs to this slice. So that's how the Merkle tree does. So it says a Merkle tree allows one party to commit to a vector of data using a collision resistance hash function by building a full binary tree where the leaves are the hashes, all the data hash is that marks the hash as a leaf, and each internal node of the tree is the hash of its two children. So we have two leaves, two of the leaves hash into one node, then those two hash into one node, just like going from, let me show you what I mean. Everybody knows what the Merkle tree is. Yeah, everybody knows what the Merkle tree is. So the root R of the tree is the commitment. So the validation part, like I said, pi I for position I, which is included in this set of numbers from 1 to t, consists of siblings of all nodes along the path in the tree from the hash to the roots. The roots R together with the validation part I can be used to prove that whatever slice, whatever shred is at the position of the Merkle tree with the root R. So once they are getting the shreds, they are also getting the root node and the validation part for that particular shred. So you compute with the root and the position of that shred if it actually belongs to this root. So that's, so the validation part is checked by recomputing the hashes along the corresponding part in the tree and verifying that the recomputed root is equal to the given commitment R. So if the verification is successful, we call di the data at position I with parts pi I for the Merkle root R. The collision resistance of the hash, blah blah blah, ensures that no data d prime I is equal to di. So you cannot forge a shred. The shred has to be actually equal. It cannot be slightly off. It has to be exactly equal, and can have a valid proof of for position I in the Merkle tree. And that's just basically what I was trying to explain, essentially. So let's go into how some of these things have been implemented in. So let me check into Agave. Let's get see here. Is GitHub search Agave Onza. So Agave is a client that runs a validator client. So it is a software that's running how you interact with the network, how you can be a validator node. That's what Agave is running. So if validator node just means you know that it's participating in voting. So they are voting or you are creating the blocks that people are voting of for. So that's just what a validator node is. And the other node is an RPC node. RPC node is a read-only node, does not vote. But it can read every state of the blockchain. Yeah. So Agave is a client that is used to implement the other clients, the expired answer. Let's talk about Agave. So this is everything, most of the thing that's happening on Solana. There's a client, and we have accounts decoder, accounts DB, banking stage, ingress. A minute. Let me zoom in. Oh, sorry. Zoom in. Yeah. Okay. We have the bank's client, bank's interface. So what we're looking for exactly? There is this validator. IPQRSTUV validator. So this is every single thing about Solana, about interacting with Solana in one place. There is this source, there is this looking for main RS. Let's see what main RS is. It's a big chunk, but let me open it locally so we can see how much has already been integrated. Like we would be able to see things like, come back here, we're able to see things like the voter. Where's it? Where you at, bro? Like things like the voter, if that has been implemented in it, rotor, and all. So let's just go down the rabbit hole. Yeah, that's what I'm here to do. Take you down the rabbit hole. CD documents, CD agave. Let's grab this one. Code agave. This is okay. So let me open this. Is there something I'm missing? Yeah, okay. Let's see. It's a big codex. Don't do that. What? History, proof of history, RPC client, SVM, score. To take it, there's a guide for exploring this repo. Let me see the guide for exploring the repo in 1 minute. Okay, yeah. Okay, so consensus network. Okay, so they're like two, as a validator node, there are like two stages or two modes that you can be in. So either you are a leader, like we talked about, or you are voting for the block. So there are two types. There are two important parts, which is the TPU and the TVU. The TPU is the transaction processing unit, I think. So let's get to TPU. I think that should be inside core. So that is basically that part of this program, that part of this software only executes when you're a leader. You can only have access to that part of it when you're a leader. That's where you create the blocks, you create the slice, the shreds, broadcast to every other node on the network. And that's when you're in validator mode. That's when you're in leader mode. That's where you have there. So it only executes when you are a leader. I think it should be inside. Yes, core. Inside core, we have source. Inside core, we have source. We have, I think, what's it? Main RS. Okay, validator. Not that one yet. Librs, not Librs. Let's check Librs. Should not be Librs. Not Librs. In the what am I even looking for? Okay. Back to banking stage. Consensus. Let's check consensus. We have vote stake, tower stake, banking stage. No, not this one. I think 1 minute. Let's check the TPU itself. RSTPU client. So TPU client, not blocking. TPU client. Aha. So this mode is for when you are a leader on the network. Try to see action transaction new. No, what I want to do is actually validator new. What I want to check is validator new. So let's check validator source main RS. I think it's this one, and we have a not this main RS. Bin dashboard. 1 minute, guys. TPU have want to be inside the validator new. Let me check. This is a big repo. OR new. No, OR new, OT new. Validator. CLI validator. CLI validator. Voter. Yes, validator.rs. Okay, it was inside core. So it was inside core all along. A big group you can get lost. So it's inside core. Then inside validator.rs. This is what I was looking for. So yeah, there is this validator rs, and we have a validator new function. That means this is a new instance of validator. Come on, let's scroll up. It's like 6,000 lines of code. Yeah, okay, this is 3,000 lines. This is not the 6,000 lines one. It's 3,000 lines. Validator. No, just do new. 197 instances of new, bro. Okay, it should be a new function. So call it 137. Okay, to be in fn new. Okay, 3, just 3. Very good. Yes, validator and new. Yeah, it's an implementation of validator. So we have new. Okay, so if this is one, let's check the comments. Let's try to pub struct validator exit log config JSON RPC service, gossip service. Yeah, I said gossip service, proof of issue recorder, proof of issue service. This one I'm supposed to read about this also. I've not read about it yet, so I can't say anything about that one yet. TPU client next runtime. Okay, by creating a new instance of validator. See you. This is node. Let me see. Node is it in the same file? Same file. Node. No. So node identity keeper. That's the keeper for this validator. Ledger part vote account. Vote account is where this source shows that you can vote. That's the account that shows that you can vote, and that's your stake. I think. So say authorize vote, constant endpoint config, validator config, check what validator config. Rust analyzer is not Rust analyzing. Let me restart the server. Fail to load workspace. You can fail to load workspace. Why are you failing to load workspace, bro? Something is broken here. Stop server first. So restart server. It's breaking for some reason. So it's not, IntelliSense is not working. Trying to check where node is imported from. So what it's doing is just self new with exit. So let's check what that new with exit is doing. See new instance of validator new with exit. Okay, just below it. My bad. Debugger session is enabled. Validator TPU config is from this TPU config. Start time is now. Adjust no file limits. I don't know what that does. Free and thread pool builder. Trying to see if most of the things that we talked about in Alpenglow are already in here currently. For the validator, so we want to see things like rotor. Let's check the import if there's rotor something or voter anywhere here. Slack client, Slack gives our gossip. Measure POD, runtime, timestamp. This is a big, humongous repo. Let me see. Rotor, is the rotor in this file? Not, yeah. I don't think rotor is implemented. Votor, yeah, I think that's votor, yeah. Okay. So votor has been implemented currently. Agave votor, yeah, okay. So vote trees. I think we have, and this was the one it's called Alejandro was talking about, that's enabling XDP. We'll talk about that maybe on Friday or something. So voter, let me see, voter, what else? Finalized, voter event sender, bounded. It's a big repo. So let me try to see if I can explain what's going on here. Maybe not. So we know that voter has been implemented here. So from Alpenglow, the voting component voter finalizes block in a single round. So yeah, this one has been implemented. We saw that. Biotic rotor has been implemented yet. I don't think it has been implemented yet. Okay. Okay. Okay, let's see. What other things are we familiar with here? Familiar from the repo block store. Yeah, I think we saw block store here. Block store. Block store. What's that? I think it's block store. Yeah, this one. Block store. See the block store component, the block store. We drive up and go block store. It's a block store. Block store collects and stores the first block received through the rotor in every slot. So the first block that is received through the rotor is stored inside blocks. But I don't know if this exact one is the block store that we saw here. Let me check. Block store. Let me do Ctrl Shift F and find that. No, not this one. So it's not the exact one. Or it was intentionally spelled that way. Okay, block store dot clone. Bro, I know me that my Rust analyzer is not working. Try to see if I can do that. It's not working. I'll fix it before the next live stream. So our aim now for the next part of this live stream is we're almost done now. But for the next live streams would be maybe Friday, we might take more time. Be going over as much as we can sink our teeth into here on the validator. So we'll just be going over this agave repo, this huge, humongous agave repo, trying to understand everything that's going on inside of the repo. And I'll try to explain as much as I know. And guys, just comment in the chat if feel you want to explore some other parts of it I've not talked about. And all. Did I get? I don't think I got any request to entry. Yeah. Okay. So far, what have we talked about? I did a revision on what we did on Monday, and we tried exploring. We tried to see how much of Alpenglow, like what are we familiar with in Alpenglow that's already inside of the Agave client repository. See, yeah. And we explained the Merkle 3 approach. We explained erasure coding, explained signatures, aggregate signatures, and yeah, I just skipped all this one because we've talked about them on Monday. So you can Monday was yesterday, no, 2 days ago. Today's Wednesday, yeah. Yeah, today's Wednesday. So you can just go over the Monday's repo. That Monday was actually me raging out, trying to figure everything out, but you can still get some insights from that part of the video also. And yeah, I hope you're now more confused than when we started the video. We'll figure this shit out together, guys. But yeah, this has been today's episode of the Anchor Founder. Uh, let's see, a minute. Okay, let me see. Do we still have? What else can we do? What else can we do before we call it a day? Yeah, I want to go over this cryptographic techniques, not cryptographic techniques. This one, encoding and decoding the function encode takes. We've talked about encoding and decoding previously. But let's see. This function, the function encode takes as input a payload m of size small m. It erasure codes m as this is just explaining how encoding and decoding works. Okay, so it erasure codes each slice. So this is one part of the data, second part, different slice of the data. It erasure codes each slice and builds a Merkle tree with root R, where the leaves are ashes of D1 up to DT. The root of the tree is uniquely associated with M. Yeah, it returns R, whatever this is. Explaining mathematical expressions are something else. So where this is just basically explaining what they talked about here. Where each D1, DI, where each D is the data at position I with part pi for the Merkle root R. So this one summarizes it. The function decode takes as input same thing, where this weird symbol is a subset of this set of size this, and each data of correct length is the data at position I with moreover, a decoding routine makes sure that the root R is correctly computed based on all data pieces that correctly encodes some message M, or it fails. If it fails, it guarantees that no set of data pieces associated with R can be decoded and that R was provably maliciously constructed. So this decode is trying to point out if something was maliciously constructed or not. So to ensure this pass or fail property, the decoding algorithm needs to check for each reconstructed data piece that it corresponds to the same root R. More precisely, the code reconstructs a message M from the data. Then it encodes M as a vector and builds a Merkle tree with root R with the ashes as leaves. If R prime is not R, then the code returns M prime, otherwise it fails. Yeah, basically what we've talked about the Merkle tree. Let's see what it looks like in the chat. Okay. In this section, we describe Alpenglow protocol in detail in the Alpenglow protocol. Okay. So we have block store. It should start from broadcast. Let's block store where you're starting to voter, the block store to the pool, block creation, rotor, back to block store, pool broadcast back to the pool, voter. Okay, I think there should be more. This should make more sense if we go down. Overview of the components of Alpenglow and their interaction. Arrows show information flow. Okay, these are just different parts. It's not like a sequential order because I was looking at block store shouldn't come first. These are just different parts. There's a block store, there's a repair, there's rotor, there's voter, there's a pool, there's block creation, and there's broadcast. And all of this interact with each other in the way that the arrows are shown. Okay. Block data in the form of shreds. So block data are blue shreds. So these blue lines are block data. Internal events are green. So internal event like the voting event, the voting. Okay, sorry, votes are red. Votes and certificates are red. Internal events are green. So this is a vote. This is a vote or a certificate. So either you're voting or passing a certificate somewhere. So that's the red one, and the green one are the internal events between that's happening in the protocol. That's happening within one node, like inside a node, the events that it's doing. So it's by passing events to to itself. Thread, slice, and block. So we have a hash, is a root node. So starts off from this is slice one, slice two, slice three, the full block. Okay, I think this is the correction of one misconception I had. So D1 first data, D2 is encoded into R1 up to DT, D1, D2. So each slice is a full slice is a it's what's it called? Yeah. So each slice is the root, is a leaf. So this is one slice. So some data of this inside the slices, that's the shreds, are build up to form one node. So this second slice also from other node. Is this actually oh is looking awkward. It's looking this is saying each data slice here is part of each data slice here. I thought it was each shred that is erasure coded here. Each shred, I thought it was each shred that computes to become each shred is it's called each shred has its own Merkle tree, is what I thought. But now we're saying each slice that is part of the block are what forms the Merkle tree. We will look at that. That's still one misconception I've not figured out yet. Hierarchy of the block data, visualizing double Merkle construction. Oh yeah. So this is root one. This is root two. So every slice, yes, I was correct. So every slice would have its own root. The next slice has its own root. The other slice has its own root. So all of the slices have their roots, and all of the roots would also be leaves or nodes that will become one final hash. Okay, so we're correct. So it's double hashing. So say we have chat, we have chat, do we have chat? We don't have chats. Okay, no chats yet. Aye. Cool. Let me see. Right, blog data. Definition one, shred. A shred fits. Okay, let's read this. Each slice has a Merkle root, which are in turn the leaf nodes or the second Merkle tree, where the root corresponds to the block hash. Yeah. A shred fits neatly in a UDP datagram. It has the form STIZTRTDI. What all of that means is STI all through N are slot numbers, slice indexes, shred index, respectively. So this is slot number, slice index, and shred index. Cool. Yeah, like I said, there needs to be a data part, a part that you can use to reconstruct the Merkle tree to be sure that this is actually part of the Merkle tree. So S is slot number, T is slice index. So what index of slice? This is slice one, and what index of the shred is also this. So ZT all through 0 and 1 is a flag. It's a flag. What flag is it? See definition 2 below. Definition 2. A slice is the input of rotor. See section 2 point. Why am I seeing different sections just to understand what you're talking about? Okay. They're explaining what rotor is. Given any data shred of total shreds, we can decode the slice. A slice has the form. Okay, let's finish this. Di is data at position I with part P pi I for the Merkle roots RT. Then this is sigma, I guess. It's sigma. I think it's sigma. Sigma is the signature of the object slice STZTRT from the node leader, which means signature of the object slice of the object. So each okay. Sigma is the signature of the slice. That's what it's saying. It's what it's saying basically from the node leader. So each slice. Okay, I think I understand that part. A slice is the input of rotor slice is the input of rotor. Is the input of rotor. Shouldn't a slice be what is going out from the rotor? Section 2.2. Given any parity, I think this data shred is not parity shred. Is it data shred or parity shred? We can decode section 1.6 slice. A slice as the form, this form, where S is slot number, T is slice index, ZT the flag. Yeah. RT is who knows? Define RT. Okay, so STZTRT. Okay, ZT here is the flag. Then RT, what does it define RT? Merkle roots, that's the Merkle roots. Okay. A slice as the form. So this is how a slice is expressed as, where S, T through N are slot numbers and slice indexes respectively. We talked about this already now. Slot number and slice index already. Okay, just explaining what a slice is. Where ZT through 0 and 1 is a flag indicating the last slice index. Flag indicating the last slice index. Okay, the index of the last slice. So MT is the decoding of a shred data. Okay. For Merkle root RT, then sigma T is the signature of the object, of the whole object slice from the node leader. A block B is a sequence of all slices of a slot here for the purpose of voting and reaching consensus. Okay, a block is in the form of what a slice is. Yeah, from index 1 to index k of all the slices. So this is one slice. Yes. Yeah, this is one slice representation. So a block is just a couple of different slices, where zk equals 1, zt equals 0. For t less than k, the data of the block is the concatenation of all the slice data. Find slot b equals slot s. Block data M contains information about the slot parent and hash parent B of the parent block B. The average limit on a block, for instance, each block can only have a bounded amount of bytes. Okay. And the bounded amount of time for execution. All right, that makes sense. We define hash B of block B as is a slice. Yeah, okay, this is one block. The hash of the block as the root of a Merkle tree. So the hash of a block is the root of Merkle tree, big T. So T is a complete full binary tree with the smallest possible number of leaves, M, with M being a power of 2, such that M is greater than or equal to K. Okay, the first K leaves of T are R1, R up to RK. That means the first leaves of the block is also root ashes of the Merkle tree of the shreds. No, the shreds in a slice is also one Merkle tree. Then each slice is also a leaf of a bigger Merkle tree that B prime's parent and B prime's parent's parent, and so on. So if B prime, this is not prime, so that's why I misread that. If B prime is an ancestor of B, then B is a descendant of B prime. Yeah, relativity. Note that B is its own ancestor and descendant. If B is its own ancestor, why is B its own ancestor? If B prime is an ancestor of B, then B is a descendant of B prime. How is B its own ancestor and descendant? When it's a descendant of something, is it its own ancestor? Okay, let's see. It's be an ancestor of something. Okay. If B is the last root, it's its own ancestor. Yeah, and it's its own descendant. There's no descendant. So maybe that's because it's the last root. It's a descendant of B prime though. So I don't know this. Let me validate this. I get try to validate this. Let me see. Let me see. Let me see. ChatGPT. I just use ChatGPT to go over. I attach the PDF in ChatGPT thread, and when I have questions, I just ask ChatGPT. Codex. Where you? So okay, we are 20 minutes past time already though. Let me just close it here. I think it's been chaotic so far, and that's good. Rota is the block dissemination protocol for Alpenglow, the leader sender wants to broadcast a block. Yeah, this is a very interesting piece, and it's nice that we're actually getting into it. So on Friday, we would have a lot of summary to give for everything. I hope I've finished everything by Friday, hopefully, and I can give a summary without going back and forth with ask questions. But for now, if you have any questions, I'll have to direct the questions to the writers of this white paper. Yeah. So yeah, that has been the Anchor Founder, guys. Thanks for hopping on. As always, I will meet on Friday. Peace.